Okay. Today we have,
Thank you, sir.
welcome. So we'll be looking at graph theory. So we'll be looking at the various definitions of a graph. So first of all, we'll look at why do we call graphs some names? Why do we call a graph a simple graph, a multi-graph, a pseudo-graph, a directed graph? Then we'll determine what we call the degree of a vertex and what is called the degree sequence. And then prove the handshaking relation or theorem. And later we'll look at the adjacency matrix of a graph, and then what you call the adjacency list. And then getting to the end, we'll look at how do you calculate the reachability matrix? And how do you use a search, these two types of search, breadth first search and the depth first search when you are giving a graph. This one, normally I leave it for the computer scientists. But if you want to know how to use the Dijkstra's algorithm to find the shortest distance between 2 points, we'll take an exercise subsequently later on. So that's the plan for tonight. Okay, so let's do some background. First of all, the Moodle platform is now working. The ERP is working. The Moodle platform is working. I have updated the Moodle platform with the following past questions. I sent the past questions, I think, yesterday. I don't know why this is not opening. Okay. So, so if you can access your Moodle platform, you should see that I've updated it with the past questions I sent to the reps. Okay, so after topic 9, go down after topic 9. Yes, if you see topic 9, after 8, you see that what comes is a folder made up of past questions. So you see this folder, and there are past questions made up of 2014 to 2016. These are the old format of past questions, and it comes also with a marking scheme at the end. But yesterday I added from 2019 to 2021. So these are last year's papers. So we have one question made up of a face-to-face exam. The 2019 was written face-to-face, and 2021 was written as a take-home. So I want you to look at the format of the questions. You see that for online exams, the questions are a lot. But for a face-to-face, you have to work within 2.5 hours. So I will have to do a blend. I may not have to ask all these questions. So just take note of it. Today we are going to solve questions from BIT, DIT, past questions in graph theory. All the questions are already on the page. Okay, so please take note of this. And so all the submission portals too are open. So at the end of today, assignment on graph theory is already activated, so you can submit a group assignment on graph theory. And then the others are still running from algorithm all the way. all those exercises around it. Today, I won't give you any questions on Socrates. I'll just have to give you this group assignment, which you will work with. Okay, so that is the plan. We want to now look at what makes graph a graph. Why do we call graph these specific names? Okay, so I'm going to go straight to my PowerPoint, and we are going to take it from there. Not my, I'll come back to the PowerPoint. I'm talking about my Excel, but let's take the history behind graph theory. Okay, now graph theory actually started when this gentleman known as Leonhard Euler, he was a Swiss mathematician, and he was trying to study a problem of how to connect bridges that were on a particular river in the former Republic of Russia. Okay, there was a town called Königsberg, and he wanted to find out how do you connect all the 7 bridges on the river, and the search for a path, or the search for to cross that river using what we call a transversal or path, brought about the study of the structure of the World Wide Web, which now is an application to graph theory. Finding shortest distance between 2 cities. We saw this in algorithm, molecular structure. Okay, so Leonhard Euler, in his search, this was a problem. This was a city, and this was a river, and the river has 7 bridges. It's been highlighted as red. We simplified it to a graph that looks like the picture on the right. We called it the 7th bridge of Königsberg. If you're able to get the path starting from a point and go over all the 7 bridges and do not go over one bridge more than once, then you have found what we call an Euler's path. Okay, so this is actually how the whole study of graph theory really started. That gentleman brought a revolution to the study of this subject, and today we are using it to do all sorts of things. Okay, so this is the face of Euler, and we are going to study a few of the things he did. Now, so the applications are a lot, so many applications, but I've listed a few of them. But I like the ones at the end: computer representation of algebraic expression, how to use basis of database and data mining, how to use internet and internet router networks, compression coding, finding route finders like Google Map, computer game playing, computer graphics like 3D Mesh, all these applications to graph theory. Okay, so it's one large subject, but we're just going to take a chunk of it and find how we can solve questions underneath it. Okay, so the first part of the lecture is to find the names of the graph. Graphs are determined by the shape. So when you see a graph and we say it is called simple, there's a reason why we call it simple. Now look at the definition. Now a graph is called simple if the lines joining the vertices, remember a graph is defined by vertices and edges. So if the lines joining the vertices are just single lines, in other words, it doesn't have what we call a self-loop, or it doesn't have multiple edges, then it's called a simple graph. So a simple graph is simply a graph that has no self-loop or para edges. Okay, so a rectangle having four corners and 4 edges is a simple graph. A triangle having 3 corners and 3 edges is a simple graph. Okay, so anything that the corners are joined by just lines, single lines, we call them simple graph. Now, but if the lines joining the vertices are more than 1, we call them multi-graph. So if you look at on your screen, I have 2 graphs here, G1 and G2. Now, if you look at G1, between vertex 1 and 2, there are 2 lines. We call them multiple or para edges. Multiple edges or para edges. So this graph G1 is actually a multi-graph. But G2, a square, is actually a simple graph because the vertices A, 1, 2, 3, 4 are joined by single lines, okay, and the diagonal. Now, if the graph happens to have what we call a loop, a self-loop, then it's called a pseudograph, okay, a pseudograph. So an example of a pseudograph is this. Okay, at point T, there's a loop. At point W, there are two loops. So pseudographs consist of self-loop. Okay, so the three graphs: simple graph, multigraph, and pseudograph. Now, when any of these graphs I've shown you happens to have direction, it means that if you look at a simple graph and there's an arrow showing you which vertices you are leaving and which vertices you are going to, then we call the graph a simple directed graph. If it's a multi-graph and there are direction, we call it either a multi-directed graph or a directed multi-graph. Doesn't matter. The order doesn't really matter. Okay? If it's a pseudograph and there are direction, we will call it a directed pseudograph or a pseudo-directed graph. Okay? So let me see whether you can make sense of all this. Let me try and give you some pictures and tell me what do you think they are. What type of graph is example 1? What graph is this?
Simple graph.
Simple. Okay. What about 2?
Multigraph.
Multigraph.
Okay, multi. What about 3?
Pseudo.
And what? There are arrows.
Pseudo-directed.
Pseudo-directed. Okay. What about 4?
Pseudo-directed.
Multi.
There's multi. What else do you see?
A simple.
Pseudo.
It's not simple.
Simple.
Pseudo. Pseudo.
It's not pseudo.
Pseudo-directed.
Pseudo-directed. Okay. So there is a multiple edge. Look at D, C, and D. And then there's a loop. That is pseudo. And then there is a direction. Okay?
Mm-hmm.
So what about this graph? What type of graph is this?
Multigraph.
If you tell me multi, then you have to show me 2 lines joining 2 points.
No, I said this is simple. This is a simple graph.
Simple graph.
Simple. Okay. What about this?
This was
This was simple graph.
It's also a simple.
Okay, it's a simple graph.
Also simple.
It has something that we will talk about later. The lines are numbered. There are numbers on top of the line. Okay? These numbers are actually weights or distance. So we call them weighted graph. It's simple, but it is weighted. Okay? Simple but weighted graph. Okay. What type of graph is this?
Multiple directed.
Yeah, this is multiple directed.
Multiple studio.
no
Okay.
multiple seated.
Multiple or multi-direct.
Directed.
It's not pseudo. There are no
Multi-directed.
There are no loops. Multi-directed.
I think now
Simple
everybody
directed.
knows the definitions of the graph. Okay, now let's go to the next definition. The next definition has to do with the degree of a vertex. The degree of a vertex. Now, when you're giving a graph, the lines, the number of edges connected to the vertex or the corners is known as the degree. Okay? And we write it as deg of V. Now, if it's a simple graph, then we have degree of the vertices. But if it is a directed graph, then you have what we call out degree and in degree. What is an out degree? It's actually written as deg plus of the vectors. Is the number of edges that are leaving the vertex.
Or outside.
Yes, they are leaving the vertex and going out.
Yeah. Yeah.
And then the in degree are actually number of edges arriving or coming to the vertex. And we normally use deg minus of V. When you add the in, those are coming in, okay? And you add it to those who are going out, it gives you the degree of the vertex. Okay? So the total degree of the vertex is find the in and the out. And that will give you the total degree of the vertices. Okay? We are going to take examples so that these definitions become clearer. So let's take the first example. I'll come back to degree sequence and then isolated vertex. Let's take this graph. Can you tell me what's the degree of each of the vertices? So deg S, it means what's the degree at S? How many lines are on a S?
2, not 3.
Three
No,
lines.
Three.
What about T?
1,
One,
What about U?
2,
two,
Two lines.
What about V?
4.
Three lines.
It's
No.
4 lines.
Four lines.
Okay. What about W?
2,
Two lines.
Okay. What about G?
0.
G, 0. Okay, so now let's do some definition. When you have a vertex that do not have any line connected to it, it's called an isolated vertex. Okay? Now,
Yes, sir.
based on what we have done, when we sum all the degrees of the vertices, it will give you summation deg of. And so this is actually the summation of from S all the way out to G. And
12.
then it gives us 12. So this is the degree of this graph. The degree of this graph is 12 because it's actually the degree of the individual vertices. Now let's count the lines, the edges. How many edges do I have?
6.
There are 6 of them. Okay?
Yes,
So I
sir.
get 6 of them. Now,
There are 6.
according to a method called the handshaking theorem, the handshaking theorem says that the summation of all the vertices, the degree of all the
The
vertices,
vertices.
okay, should always be equal to 2 times the number of edges.
Edges. Okay.
Okay, so
Yes, sir.
now let's prove this. When we sum all the degree of the vertices, we got 12, isn't it?
12.
Yes, sir.
Yes, sir.
And then when we counted the edges, we got 6. Now
6.
multiply 6 times 2. Is it not equal to 12?
Yes, sir.
Yes, sir.
Yeah, so this is what we call the
Handshaking.
handshaking theorem. It's called HST. So when he asks you to prove the handshaking theorem, you take your time and find the degrees of all the vertices, add them, then count all the lines, and then show that twice the number of the lines will give you the total degree of the vertices. Okay, I hope you can remember
Yes,
that.
sir. Yes, sir.
Let's define what we call degree sequence. What is a degree sequence? It is the list of all the degrees given arranged in ascending order. And then add the add-
Charlie.
so let's pick all the degrees of the vertices that we got here. So arrange these degrees we got here in ascending order. What will be the first one? Paul, you raise your hand. What's your question, please? Unmute yourself.
I was talking about the edges that you said is 6. The 6 edges. I
Yes.
just want, where is it including the G?
The 6 are the lines. So we are counting the lines in this graph. So W to S is 1, W to V is 2, S to U is 3, U to V is 4, S to V is 5, and then V to T is 6. So these lines, the edges, okay, it gives us 6. So that's how we are able to prove the handshaking theorem. Okay, now, so let's now list the degrees in ascending order. The vertices, what is the smallest value?
0,
0, followed
1.
by 1.
2.
Now 2 occurs how many times?
Twice.
Twice, okay. Then
Then
3,
3 and 4.
and then 4. So this is what we call the degree sequence. Okay?
Yes, sir.
So this, when you are giving a question, they ask you to find the degree sequence. All you need to do is arrange them in ascending order. Okay. Now, let's take another example. Before I do, okay, well, we'll look at another example here, but let's define another term. There is something called adjacency matrix. Adjacency matrix is simply an n by n matrix. The n is the number of vertices. Okay? So for example, if you pick the one we just did, this one, this graph, if I want to find the adjacency matrix, I'll call this A into bracket G. I'm going to list how many vertices I have here, starting from in alphabetical order. So I will start from G going to S, T. Then I have U, then I have V, then I have W. So I have 6 of them. Okay? I have 6 of them. And then you are going to map them to themselves. G, S, T, U, V, and then W. Okay? The same thing. So we are going to form a square matrix out of these vertices. And the values you are going to use are actually based on the way the lines are connected. So when you take A to A, is there a line joining A to A? Sorry, we don't have A here. If we take G, is there a line joining G to G?
No, please, 0.
You put 0. Okay? Now then you go and look at the line from G to S. G is an isolated vertex. It doesn't connect to anything.
Anything, yes, sir.
So G to S, G to T, all will be 0. G to T is 0, G to U is 0. All these will be 0. All of them. Okay? Now let's come to S. S here is connected to W, it's connected to U, and it's connected to V. So S to U is true, 1. S to V is true, 1. S to W is true, 1. Everything else,
0.
Okay?
Okay.
Now let's look at T. T is only connected to V. So V will be true, everything else will be 0. Now let's take U. Now U here is connected to S and it's connected to V. So S is true and V is also true. Everything else is 0. Then let's come to V. V is connected to U, to W, to S, and to T. Okay, so this is 0. It's connected to S, that is true. It's connected to T, that is true. It's connected to U, that is true. It's connected to W, that is true. V is not connected to itself. There's no loop there, so that is 0.
0.
Okay.
Now look at W. W is connected to only two vertices, to S and V. So S is true, and then V is also true. Everything else is false. This is what we call adjacency matrix. Okay? And then when he asks you to find adjacency list, you only pick G and find out the only place it's connected to. So you see that if you are finding adjacency list, we say G So look at this matrix. G is not connected to anything. Normally, this is what I do. I'll use an arrow and I'll say G is, sorry. Send this as a formula. Okay, so let me just leave it. G is not connected to anything. Let's come to, let's come to S. S is connected to which vertices? Connected to U, V, and W. I'm going to write U here, V here, and then W. Okay, then we come to the vertex T. Okay, where is T connected to?
V.
T is like G.
Is connected to B. Okay, what about U? U is connected to what?
S,
S
and V.
S and V. And then when we come to V, V is connected to S,
S, T, U. S, T, W.
Okay, so S, T,
And U.
U, and then W. Okay? Then the last one, W, is connected to which one?
S
and V.
S,
S, and V. So you place these things in a nice matrices form, and then you show an arrow, give them a nice arrow, telling you that these things are connected to this. This is what we call adjacency list. Okay, this is what we refer to as adjacency list. Okay, so now we know what these two are. Adjacency matrix, which is made up of zeros and ones. Adjacency list, which is made up of what is connected to what. You need this to be able to do a whole lot of questions. So let's pick the next example. Now, so for simple graph, sometimes you may have a value like 2. You use the value 2 if there are multiple edges. Okay, that's the only thing that you see in adjacency matrix. So let's look at this graph. Now, if you take A is not connected to A, there's no loop there. So A to A is 0. Now, A is only connected to E and D. So this is what I'm going to do. D is true, E is true. Everything else is going to be 0.
0.
Now, B is connected to only D here, and the values there are 2 lines. So I'm going to place the value 2. I hope you understand. We say you use the value 2 if the line joining the vertices are multiple edge. Okay? This only occurs in simple graph. In directed graph, you have a direction. So you know where one is going, one is coming. But for simple graph, there's no direction. So you count the lines 2, that's all. Okay, so B to D is 2, and the rest are going to be 0. Okay, now let's come to C. C doesn't go anywhere, it's an isolated vertex. So we just have to repeat the zeros throughout for C. Now D goes to A, it goes to B, and it goes to E. Okay, so D goes to A, it goes to B, B is 2, and it goes to E, and that is 1. Everything else is 0. And then E goes to D, goes to A, and comes to itself. So EA is true. E doesn't go to B, E doesn't go to C, but it comes to D, and it goes to itself. Okay, Sadiq, what is your question, please?
Yes, sir. Good evening, sir.
Yeah.
Sir, please, can you hear me? Hello, sir.
Yeah. Yes, I can hear you. Go ahead.
Okay. So I thought the adjacency matrix, I thought we were dealing with only ones and zeros.
Yes, but it's only for simple graph. Okay, that sometimes you get the value 2. Okay, look at the definition. For adjacency matrix, for simple graph, you have an n by n matrix, and the values are 1, 0, and 2. 1 is if there is a line joining the vertices, 0 is there is no line, and then 2 if there are multiple edges. Okay, now,
yes,
the reason why I'm showing you this, when you come across this one, for example, something like this, between D and E, look at it, this is a digraph. So for directed graph, if you are finding adjacency matrix, if I come to, let's say, D going to E, you see DE here, because it's leaving, I'm going to put 1 here.
Okay.
Okay. And then when I come to E coming to D, E going to D here, I'm also going to put 1 here. I won't put
1 there. 2. Okay. Yes, sir.
So there is a difference. It only occurs only in simple graphs.
Okay.
When there
but
are
when
no,
it's directed, and when
with
it's
directed,
directed,
you will see that the only is reduced to zeros and
1,
ones.
1. Okay,
Yeah.
sir. Okay, sir.
Okay. Now,
Thank you,
so
sir.
now let's finish the question. Now let's find adjacency list. Now we know that this graph, A is connected to D and E. So I'm going to add here D and E. Now B was connected to D only. So this is going to be D. C, this does not go anywhere because it's isolated. And then when you come to D, D is connected to A, B, and E. So it becomes A, B, and E. Try and make sure you do this in alphabetical order. And then E goes to A, it comes to D, and comes to itself. Okay, then we want to prove the handshaking theorem again. Now, degree of A, the lines incident at A, how many lines are here?
Sir, 2.
2.
lines.
Okay. What about B?
B,
Sir,
2
2.
lines.
B is 2.
Yes, 2.
Okay, now C we know is 0. What about D?
D is 4.
It's 4.
4.
He's
Okay.
4.
Now look at E carefully. Somebody tell me how many lines are incident at E?
3.
3.
Okay, now let me give you a hint. When you find degree of a vertices, you should always get an even number because of this formula. Remember what I showed you in methods of proof. 2 times any number is an even number. So this should always be an even number. If I put 3 here, this is 11. So there's
Yes.
something wrong with this. Who can tell me? E is not 3 actually.
Sir, it's 4.
Okay, how do you know it's 4?
Yeah, because from E you go to A, then D, and it starts from itself and come back to itself.
Yes, start from itself and come back to itself. So the loop, please pay attention. When you are finding degree of vertices, the loop is counted twice. It leaves and it comes for degrees of vertices. Okay? When you are finding degrees of vertices, you count the loop 2 times. So it is leaving, that is 1, and it is coming. That gives you the 4. But please, when you are counting the lines, the edges, when we come here and we are counting the edges, a loop is not counted twice. It's counted as a line, like a circle. That's a difference. I hope you remember. Okay? When you are counting lines or the edges, a loop is counted as a 1 line, even though it's leaving and it's coming. It's only when you are counting degrees of vertices, a loop is counted twice. Okay? So how many lines do we have in this graph? A to D 1, A to E 2, B to D 3, B to B 4. Okay?
6.
And then you have what? D to E 5, and then the loop is counted as what? 6.
6.
But we are able to prove a handshaking theorem. 12 is equal to 2 times 6. And that is a handshaking theorem. So this rule, this handshaking theorem should always help you to know when you are making a mistake in the degree of vertices. You can always cross-check and be able to tell. Okay, let's do one exercise on degree of vertices, and then we will go and look at the next set of definitions. In this question, you are supposed to find the list of all the vertices, find adjacency matrix, adjacency list in this graph. Okay, so let's take our time and find these. What are the list of vertices? How many vertices are in this graph? How many vertices? So who can help me? How many vertices are in this graph? It means how many corners are here?
So we have 5.
Okay, let's list them. A, B, C,
A, B,
D,
C,
and E, isn't it?
Yeah.
D,
Okay. Okay, so the number of them is going to give us 5.
and E.
Okay? So this is how we got the 5. Now let's look at the edges. How many edges?
Yes, sir.
Now you can use the arrows to tell you where it's going to. So edges is A to B. You see an edge like that. Then you go to A to D and have A to E. Okay?
That's 7. 7 edges.
Okay, I'm coming. Let's find now. Let's come to B. B doesn't go anywhere. The vertices, the lines are coming to B, but B doesn't go anywhere. So B to anything, I don't have it. Let's go to C. C goes to B, and then C goes to itself. And when we come to D, B goes to E, and I think that's all. Then when you come to E, E also comes to B. Now when you count these, you get 1, 2, 3, 4, 5, 6, and 7. So again, the number of lines or edges are 7. So now it means that when we find degree of all the vertices, we should get 14 based on what we've got here. Okay, I've seen a hand up. Ifa, what's your question, please?
Good evening, sir.
Good evening.
Sir, please, the D. No, one line is good from D to E, and then from E coming back to D.
Yeah, I did it. You see, you saw it here. There's D to E, that's one.
Okay.
Then also
Okay.
D, and then E to D. So I have all of them. This one and that one. Okay, but one is leaving D, the other is coming to D. So DE is leaving D, and then ED is coming to D.
Okay.
So I covered all of them. Okay, now let's find degree of vertices. Now, I should have given you in degree and out degrees, and then we would have found all the, but I have done them deg of A. So if I ask you to give me deg of A, means lines that are leaving and lines that are coming. So what is deg of A? How many lines are here?
3.
3. What about deg of B?
Third.
B,
B. How many lines are coming?
B, 2.
2. Okay. Then C. How many lines are leaving? How many are coming?
3.
So that'll be 3.
3.
Supposed to be 3,
2.
isn't it?
That's 3.
Yes.
2 are leaving and 1 is coming.
Yes.
Do you agree? 2
Yes, sir.
lines are leaving and 1 is coming back to it. Now, what about D? How many lines are leaving? How many are coming? You add them together.
3.
2. 1 is leaving.
3,
2.
3.
Okay, 1 is leaving and 2 are coming. So 3.
3.
What about E? How many lines are leaving? How many are coming?
3.
There are 3.
Okay,
1 is leaving, and then 2 are coming.
good. So you see that 14 is actually 7 times 2. So we are correct. Now let's find adjacency matrix and adjacency list. A is going to B, is going to E, and is going to D. So A to B, A to B, and A to E. Now the rest will be zeros. Okay, that's for A. And when we come to B, B doesn't go anywhere. You look at it, B doesn't go anywhere. So B to A, B to B, B to C, all of them will be 0, 0, 0, 0, 0. Now look at C. C is going to B, it's true, and C is coming to itself, it's true. The rest are zeros. And then D, D is only going to E. Look at it carefully, it's going to E. So D to E is 1 here, everything else is false. And then when you come to E, E is also going to D, that's the only value. Everything else is 0. So now let's pick where we have the ones and then write their vertices. Now A is going to B, and is going to D, and is going to E. So that'll give me my list connected to A. Then when I come to B, B doesn't go anywhere. When I come to C, C goes to B,
B and C.
B and C. And then D only goes to E, and then E only goes to D. Okay? So these are the definitions for graph. Now, the next example, we are going to define what is called reachability, and then we'll look at BFS and DFS. Okay? So those who came late, these are the things I plan we'll do. Okay, there's another matrix called incidence matrix. It's similar to adjacency matrix. An example will explain. An incidence matrix is simply mapping the vertex to the lines. Okay, incidence matrix, you map the vertices, n vertices to the m lines. Now, so if you have a graph on the right like this, what I'm mapping are the vertices A to E to the lines. The lines have been numbered line 1, line 2, line 3, line 4, line 5, and line 6. So when you take A, is A connected to line 1? You are going to put true there. Is A connected to line 2? If it's connected, you write true. If it's not connected, you write false. So it's just like the adjacency matrix, but this time it's called incidence matrix, where the vertices are connected to the edges. So which edge is the vertex connected to? That's what they're asking you. So look at A. A is connected to line 1, line 4, and line 5. So line 1 is true, line 4 is true, line 5 is true. Everything else is going to be false. Okay? And then come to B. B is connected to line 1, line 3, line 2. Okay? Line 1, line 3, and line 2. Okay? Everything else is false. It doesn't connect to them. Then when you come to C, C is connected to itself. That is 6. Okay? So the line 6 is true. Everything else will be 4.
D.
Now let's come to D.
It's connected
Now,
to.
D is connected to line 5, line 4, line 3. So 3, 4, 5. 1 here, 1 there, 1 there. Everything else is 0. And then when you come to the vertex E, it's only connected to line 2, which is here. Everything else is 0. Okay? So that is called incidence graph. Okay. Now, Sadiq, you have your hand up again.
Hello, sir.
Hello.
Hello, sir.
I can hear you. Go ahead.
Hello, sir. Can you hear me?
Yes, I can.
Please, can you go over the incidence? Can you go over the incidence matrix again, please?
Okay, so the incidence matrix says that you are going to find a matrix made up of n vertices and m lines or edges. So it's an n by m matrix. Now, the number of vertices are numbered n, which are the rows. And then the number of edges are numbered m, which are the columns. Okay? So I of G is n rows mapping to m column. That is a line, a vertex map to a line. Now I'm saying that there are line 1, line 2, line 3, line 4, line 5, and line 6. So when you pick a vertex like A, they are going to ask you, is A connected to line 1, line 2, line 3, line 4? So that is A here. And then the values I'm going to put in this row is, are they connected to line 1? Are they connected to line 2? Are they connected to line 3? That's what we are checking.
Okay.
So if you're able to tell the lines that is connected to A, then you put true there. It's not connected to that line, you put false. So
there, okay.
A here is connected to line 1. You see this line is leaving A, or it's actually adjacent to A. Then line 4, and then line 5. So that's why line 1, line 4, look at line 4 and line 5. They were the only places I placed true. The rest were false. Okay? So that is how I fill the rest. B is connected to 1, 3, and 2. So 1, 2, and 3. Okay? And the rest are false. Okay? So that's how we got the incidence graph. You pick the vertex and which line it is connected to, and you click. And the rest are all false. Okay. So this is incidence graph. As for adjacency list, I hope you can do it. We've done a lot of it. A is connected to which vertex, and B is connected to which vertex. A is connected to vertex B, vertex D. Okay? These are the two places. So A is connected to vertex B and vertex D. A is connected to B and to D. Now B is connected to A, to D, and E. So A to D, and then to E. Now C is connected to itself based on the line that you are seeing. And then D is connected to A, to B. So we have A to B. And then the last one, E, which vertices is he connected to? Only to B. Okay? So this will be your adjacency list. Okay. So we've done all this. We've defined handshaking theorem. So the next example, again, we've done in degree and out degree. You can practice this, but maybe I should do it. Some people will watch the video. How many lines are leaving A? Somebody tell me. These actually are examples in the PowerPoint. How many lines are leaving A and how many are coming?
3 lines.
3
Three
are
lines are leaving.
leaving, and 1 is
It's not that
2 are
it's not
coming.
that 3.
So 4 lines are leaving.
4 lines.
Now how many?
4 lines are leaving.
4 lines.
How many lines are coming?
2.
2.
2 lines.
What
4
about
lines are coming.
B? How many lines are leaving?
1.
1. How many are coming?
1 line is leaving.
And how many are coming? 2.
2.
2.
2
Okay.
are coming.
What about C? How many are leaving? One, two.
1, 2.
And how many are coming?
2 are coming, 1 is leaving.
2 is also coming. This is
Yes,
coming,
also.
and the loop is coming back.
Yes.
Okay, what about D? Now this is D.
2 are coming.
2 are leaving. How many are leaving?
1.
1.
1.
And then how many are coming? 2.
One is leaving and 2 are coming. 2
is coming.
Okay, what about E? How many are leaving E? Remember the loop.
3. 3.
1, 2,
3.
3.
3.
Okay.
Yes, sir.
3.
And how many are coming?
2.
3.
3.
1, 2. And what's the third one?
It's 2.
Okay, 3.
Yes, sir.
It's 2.
We get 3. It's 3. From A to E, and then from D to E, and then E to E.
E to E and E to E.
0, 0.
Okay, 0, 0. No, there are no vertices, and there is nothing coming. Now, when we add all this, we get what? 22. So now we have to count the lines and make sure we get 11. So the loop 1, this is 2, that is 3, that is 4, that is 5, that is 6, that is 7, that is 8, that is 9, that is 10, and that is 11. So you see that handshaking theorem also have been proven. 22 is equal to 2 times 11. Okay? We've done enough of this. Now, let me leave these ones for you guys to do. They are the same thing. Now, let's define reachability. What is a reachability matrix? Now, reachability is simply, this is the method in which if somebody is interested in hacking your phone or hacking somebody's phone or hacking somebody's PC, and he doesn't know you, when I say you are not a friend to that person, but how does the person reach out and get to your system? Why do your system become vulnerable? And we use this method called reachability. Now, we have what we call reachability 1. Reachability 1 is simply your adjacency matrix. Reachability 2 is when you want to find how do you connect to the vertices going through 2 paths. Remember, reachability 1 is simply going through A to B. If A is connected to B, you put through there. Okay? By reachability 2, you look at from A, where can I go to that I'll pass through 2 vertices. So A to B and B to D. So it means that reachability 2, I have a line going to A to D because I'll go through B and come to D. So we are going to take this question and then find what we call reachability 1, reachability 2, reachability 3, and reachability 4. And then when we finish, we multiply all this. The multiplication here is called the logic connective OR, and that will give us reachability star. It means that if I know the reachability of your PC or your phone, it means all I need to do is know somebody who knows somebody who knows somebody who knows you. That's all. And I will find a way of introducing an interesting virus or a picture that is attached with some virus, and I'll get your system. This is how these viruses work. They'll find your friend, and your friend will find another friend, and on and on and on. And the person they are targeting, they will get. So let's use this graph here and find what we call reachability 1. I said reachability 1 is simply adjacency matrix. So reachability 1 is just find adjacency matrix of the graph. So let's look at A. A is only connected to B. Everything else is 0. So A to A will be 0. A to B is true. A doesn't go to C, and A doesn't go to D. Let's look at B. B is connected to 2 vertices, to C and to D. So C is true, and D is true. Everything else is false. 0 here and 0 there. Now look at C. C doesn't go anywhere. So CA is 0, CB is 0, CC is 0, CD is 0. And look at D. D goes to C. That's the only place D goes to. D goes to C. Everything else is 0. So actually, your first adjacency matrix is actually what we call reachability 1. It means I can get to these adjacency matrices going through only one path. Now, can somebody tell me where can I go to from A? Then I'll go through 2 paths. one line, another line. Where can A take me to? Where can A take me to if I'm using reachability 2?
C and D.
C and D, yes, it's true. Because A to B and B to C. So C, I can go to C. And then I can also go to A to B and B to D. So C and D will be true. Everything else will be false. What about B? Reachability 2 for B. Where can B go to?
Say C and D.
Are you sure?
Say only D. Only D.
Only D. Oh.
Only D. Only D. Yes.
No, it's not only D. It's only C, rather.
Only C. Only C. Only C. Only C.
Look at it. It's B to D and D to C. How do you see it?
Yes.
That's the only place you can go to. Everything else will be false. What about C? Okay, C doesn't go anywhere, so that is. What about D? Where can D go to using 2? Again, D can't go anywhere apart from 1. You see the way D is. D can't go anywhere apart from 1. It can't go reachability 2. So everything about D in reachability 2 will also be false. What is your question?
Can I come again? Because based from my understanding and your explanation.
Yes. Where did I?
But looking at the diagram shown, I see that from point B.
Look at the arrow. From point B, where can you go to?
D.
You can go to D and then you go to C. So A, B, C is this cell. That's the only place that B can go to using reachability 2. There's no other path that B can take again that will take you to another vertex. Okay, so that's why B to C is true for reachability 2, based on the way the arrows have been arranged.
Okay, sir. Thank you.
Okay, now let's come to the next one, reachability 3. You can tell me from A, where can I go to that I'll reach? I'll use 3 paths.
A, B.
Only C.
A, B,
Only C.
D, C.
A to C.
Yeah.
Okay.
A, B, D, C.
That's the only place. Now, what about B? Can B go anywhere using 3 paths?
No.
No. Okay.
Recording in progress.
Reachability 1, reachability two. We have all that. me ask you a
Recording
real
in progress.
question. If I pick, let's say, today the person who asks me a question a lot is Eric. I've forgotten his name. Okay, Paul was Sadiq. Yes. Now, Sadiq, let me ask you. If, for example, Sadiq, I want you to draw a graph of your WhatsApp group that you are on, any group that you are on. Just find a group that there are only 4 or 5 of you on. If I ask you to draw a graph of that, can you draw it from what I've shown you? Just take the conversations you've had within the past 48 hours. Can you draw a graph of a group of 4 people in a WhatsApp group or 5 people in a WhatsApp group? Can you draw a graph where a line means you communicated within the past 24 or 48 hours? Can't you draw it? Sadiq is not talking. Okay, but Collins, you raise your hand.
Yes, sir, I'll be able to draw it. I'll be able to draw a graph of all the conversations I've had in a particular group today.
Yes, exactly so. Okay, so this is what it means. And this morning when I was teaching the group A's, I told them that I gave them a particular example. Do you remember, those of you who were following the American election, the previous past 2 elections where Bill Clinton's wife was also a candidate? Do you remember how the Russians were able to actually influence their elections? Do you remember how they got them? At least those I heard in the news. Does anybody remember that story? What did they do to Bill Clinton's wife?
They reduced the number of votes.
Hacked into her email.
Yes, they hacked into her email. Actually, like you said, they influenced her votes. But how were they able to hack into her email? Who knows what happened?
They worked through his mobile phone, through his email, and then attacked.
Yes. Yeah, but there was a particular thing she did. Maybe you don't remember. She used one of her communications. She didn't use the corporate mail. She used one of these, what do you call it? Our free email accounts that we have, Gmail, Yahoo, and all that, to send an official mail. That's how they were able to get into the system. I don't know whether you remember that news. Well, I heard this on the news, and that was exactly how they were able to. So all that we are talking about today is when you say reachability, every one of us, if you're on the net, we are vulnerable. When you post something on a Facebook page, you are vulnerable, especially if it is downloadable or somebody can send a response or you can send a response, all sort of things. Sometimes it's an innocent picture, but it's all attached with viruses and all that. And maybe it is not you they are targeting. They are targeting somebody in your circle. So this is what reachability means. Okay? So you always must be circumspect. You must always be, what do you call it? Security conscious. Most of us, we don't think too much about security because we don't think we are of any value in terms of, I'm not saying you're not valuable, but you don't, why should I be of risk? But I can tell you one of the biggest problems that people are facing is identity theft. And people can use your name to do all sorts of wicked things. Just about last week, my wife showed me a WhatsApp, a Facebook account. He responded to somebody's preaching. That was all. Not knowing those who have created that platform and they are calling friends of that so-called man of God, they were all hackers. Just like that. So even your innocent thing, you think you are doing something religious, they can target you. Well, I hope you can make sense of what we are doing. I'm seeing some hands up. Eric Wabin, Akube, Vitus, what are your questions? And Paul?
Oh yeah, just add up to what you are saying concerning all happens sometimes on Facebook, and even when you take a picture in your office and the background, the person sees the background, or maybe your Facebook account, the person will go to your mutual friend, contact the friend to get it to you.
Yeah, exactly. Exactly. So the end effect of what we are describing here, Facebook accounts behaves like, you know how Facebook accounts, we one person comments, then all the members who are your friends can see the comments. This reachability. Okay. So the way they say, look at how Gmail account works. When you are in a group of 3 and people send you a mail and one person responds, Outlook also behaves like that. If one person responds to the mail, everybody gets the response. Okay, one person responds to you will not see it as an let's say a direct mail with it will be in a chain. It will be in a chain.
Even Zoom
yes.
That we are using also have the same thing.
Okay, so you see, that's how the system has been designed. So all you need to do is to find somebody in a chain who unfortunately is not security conscious and you introduce something and then we are all infected. Okay, so that's the meaning of reachability. Now, the next application is...
I think...
Yes,
I just want to add something.
Okay.
I wanted to ask if only we normally use alphabetic order to do the reachability and then other vectors is to find the values in it. And again, I want to add this also used for security purposes, because sometimes if you want to trust somebody, you may also go to the social media and where he has been before, not necessarily his account, to locate, to trace his location for criminal activities and other stuff.
Yes, so that is why sometimes when you use Google Map and then you say you switch on your location, you must make sure that that thing can stay on and it's just locating you. I mean, you can Facebook does that thing. It tells people that you've been here. Meanwhile, people don't realize that it's automatically because their what do you call it? Their location is active, so people can track wherever you've been, and they can find out wherever you've been. Recently, I just found out that my phone has showed me all the places I've been to in the past, let's say 6 weeks or so. And when I check all those places, I use
Google.
Yes, I use Google Map to go there. And because I was going there, every active pussy or active restaurant or active hospital was now telling me, you visited here. What do you say about that? I said, did I ask you to do that? Not knowing that is also part of using that map. So these things comes with advantages and disadvantages. You may not really think anything negative about it, but like you're saying, somebody can go to your history and find out where you've been to, can easily pinpoint and tell you what do you call it? And sometimes even the type of ATM machines you use, they can track and find out you took money from here. It means this is where you are, that's where your house is. All sorts of things. Now, there's no way you can hide yourself because everything you do leaves an electronic trail and you can be traced. So just be conscious of that.
Some of the phones are even having inbuilt, like iPhone like this. It has a inbuilt system that even when you are, maybe you switch off your distance, it takes pictures that you are not aware. So sometimes it's also help Google to ask you for a tour guide or something to add pictures to a certain location that it has been updated for long.
Wow, that's what iPhone does. I'm even more afraid of that.
Yeah, sometimes with the location off, your phone is still tracking your location.
Yes, I've seen that too happen. I was on a PT platform and somebody's phone started sending nude images. This is real. And he didn't know that it was another phone communicating with his phone. And the guy wasn't aware. And when people were insulting him, somebody called him and said, look, I'm not at home. That phone is communicating with another phone of mine. All sorts of things. So just find out.
I don't like iPhone anymore.
Just find out what your gadgets you are using, what they are capable of doing, so that you don't end up in a particular place that will just put you into a situation you just can't get away with it. Okay, well, this is interesting, but let's finish up with there are 3 hands still up. Collins, Victus, and then Eric. What are your comments?
Eric, I've already asked this is I'll just lower.
Okay.
Hello, sir.
Hello.
Okay, sir. My question is this: I quite remember we treated Prim's algorithm where
Yes.
we're connecting shortest possible distances, neighboring each other to each other,
Yes.
and finding the next shortest possible distance. I wanted to say, I asked, like, how is it connected to this particular topic that we are?
Oh, it's very much connected. It's very much connected. First of all, the next thing I'm going to show you is called the breadth-first search. It's going to show you how you can search for a particular vertex using a particular method. But what you're talking about is actually the last thing I talked about that I may not do in your lecture because of time constraint. It's called Dijkstra's algorithm. It's also going to, it will pick the weighted matrix, and then we are going to find the adjacency matrix of the weighted matrix. Then we are going to pick the distance, shorter distance from one point to the other. It's a very, very beautiful algorithm. And if you're able to master that and can write a code for it, you can always use that method to determine a shorter distance in any algorithm you want. So yes, I mean, this is actually, it has a lot of application in this, but like I said from the beginning, I may not do it in this lecture. If you are really interested in it, I can find another tutorial session for that.
Yes, sir. Please, can you do that for us?
I'll see that subsequently. Today, I just want to end on BFS and DFS.
Okay, sir.
So let's take how BFS and DFS work. Okay, so again,
thank you, sir.
You're welcome. When you pick these searches algorithm, the technique here is find out what the search is doing. Now, if you pick BFS, what it does is that you visit all your horizontal members in your adjacency list. You visit all of them first. Then you go to the next layer. That's the method. So just put that at the back of your mind. I'll take an example and explain better. But when you take DFS, depth first search, this time you are going to create something like a stack. A stack is just like a vertical cell. And then you're going to place your roots where you're starting from in the bottom. And then what you're going to do is that you build a stack by going down the path of the adjacency list. This time, when you pick your adjacency member, you find the first member or the first, I'll call it the first child. Normally, that's the term I use. And then you go to the child's child, then go to the child's child, that kind of thing. Now, I mean, so use that technique to remember what DFS is. DFS is looking for a child. A BFS says that when you pick your parents, connect it to all the children. Then go to the first child, connect it to all his children. Okay, so that is the summary. Now let's take an example and this becomes clearer. So I'm going to find, first of all, adjacency list here, and it will help me to find the BFS and the DFS of this particular question. Now, so A is connected to, look at it, B and S. Obviously B connected to S based on what I have here. Now B is connected to only A. C connected to, in alphabetical order, D, E, F, and I think S. Okay? When I come to D is only connected to C. When I come to E is connected to C. And what? H. When I come to F is connected to G. When I come to G, I have F,
H, and S.
S. When I come to H is E and G. And then S is connected to A. It's connected to C.
And then J.
Okay. Okay, so now we will now concentrate on the and then use adjacency list to find my path. Okay. Now, so when I pick, they will tell you where to start from. Every question that uses BFS, they will tell you the source. So they said find your search, use this source as A to find BFS. So if I start at A, I'm going to put A in my BFS sequence, and I'll connect it to all its members. That is all its adjacency lists. That is the way you go about BFS. Pick the source and connect it to all its adjacency lists. So A will connect to B and then will connect to S. Write them sequentially in that order. Then you will tell yourself, then I have visited the vertex A. Now you come to B. B only has only one child, which is A, but A is already in the sequence. So I'll assume that B also have been visited because the child of B is already in the sequence. Then I go to S. Now S will give me A, C, G. You only add the ones that are not in the sequence. Now A is already in the sequence. So the only child you're going to add is C and G. So I'm going to add C here and I'm going to add G there. Then I come to, I'll say that I visited S. Then I come to C. C gives me D, E, and F and S, but S is already in the sequence, so I only end on F. I'm going to add D, E, and F, and I'll say that I have visited C. Then I come to G. G gives me F, H, and S. Now look at it carefully. F is in the sequence, but I don't have H. S is also in a sequence, so I'm going to add H at the end here, and we'll claim that I have visited G. Now let's take our time and see the rest, whether we visited all the adjacency members. D. D will give me C, but C is already in the sequence. It means now I've covered the adjacency members of D. I come to E. E will give me C and H. C is here, H is there. It means I will assume I've also visited E. F will give me C and G, and I'll C here, I'll G there. So again, I'll say I've visited F, and then H gives me E and G, and E is here, and G is there. So then this will be the sequence or order of searching using what we call breadth first search. And then I'll arrange them in that order. A, B, Eric, you've raised your hand. You have a question for me?
So as you were doing, you came down to pick S. Why didn't you do it A, B, C, D in that order to pick and fill the B, F, S? But you rather came down to pick S, and then you wrote the numbers that are which are not on the B, F, S. Why did you do that?
Okay, so the method, remember what I said, that when you are picking BFS, first you make sure that you pick all the horizontally and visit all the nodes of the current layer. Okay, so when you start at A, what are the nodes that A is connected to? So A was connected to B and S. So I'll visit all those people. From A, I'll go to B, then I'll go to S. I don't go to C. It's not because I say I'm following alphabetical order. The alphabetical order is only for you being able to find your adjacency list correct. The adjacency list. When you are doing adjacency list, make sure you arrange them in alphabetical order. That's what I mean. But when you are finding the search, the way they've been arranged, that's how you connect them. So A will connect to B and S. So it means I'll add A, then I go to B, I go to S. I don't go to C because I don't see C in here. How do you see it? The way, the order in which I follow is based on the way the list actually is designed, or from the graph, the way I got the list. So A gave me B and S. Then from A, I'll go to B because that's the first child of A. So I go to B. B will give me A, but A is already in the sequence. So it means that I go to the next child of A, which is S. I hope you get it. So I go to S children, and S children gave me A, C, and G. A is there, so I have C and G. So that's how C and G came in. So that means I've dealt with S. Now I come to C, and C gave me D, E, and F. So it's the way the adjacency list is connected to the vertices. And then that is how I approach my search, based on the adjacency list. So this must be correct. This part of your graph must be correct. If it's not correct, your chances are that you get some sequence, but it will not be correct. Okay, so this is what we call, yes, this is what we call BFS. Breadth first search means that this is all horizontal members. Now, interesting enough, the same but particular adjacency list can be used to do what we call depth first search. This one, you are going to visit what we call the first child only. You don't visit all of them. So when I start at A, I'll visit my first child. So I'll be placing them in a vertical stack or a vertical cell. So I'll start at A here, and then A, the first child of A is B. So I'm going to place B on top of A like this. Okay? Now, then I go to B and look at the child of B. Now, the child of B is A, but A is already in the stack. It means B doesn't have any other child to place on top of B. So this is what you will write. You will use the word backtrack. The word backtrack means that go back to the where you started from, because B doesn't have a child to add on. So I'll backtrack to A and find out whether A has any other child apart from B. And then if I backtrack, A will give me S after B. So I'm going to place S on top. Now then I go to S and look at the children of S. The first child of S is A, which is already in the stack, but it has other children. So I'll pick the next child, which is C, and place it on top of S. Remember, we always pick the first child. If the first child has been placed, pick the next child if there is another child there. So we pick C, because that's the next child of S. And then we come and look at C. The first child of C is D, so we place D on top. Then we go to D and look at the child of D. It is C, and C is already in the stack. So again, I'll do backtrack. Patricia, what is your question, please? Or you didn't realize you raised your hand, Patricia?
Sir.
Yes.
Why didn't you do?
Why didn't I do what?
The backtrack for S. For S.
No, because S still had children. You get it? When I got to S, the first child of S was A. A was in the stack. So I had to find out whether S had other children. Okay? If it didn't have any other child apart from A, I would have done backtrack. The only reason why I backtrack from B, for B is that B only had one child. And it was already in the stack. That's why I backtracked to A. But S had other children, other adjacency members. So I had the option of picking the other one. That's why I added C on top here. Okay? Okay, now we are D. And I'm saying that when we go to D, D gave me only one child. So you see what happened. It doesn't have any other child. So I backtrack. I come back to C. And then I go and pick the next child of D, C, because C has so many children. Okay, I only pick D, so now I can pick the next child, which is E, and put it on top in the stack. Okay, now then I go to E. The child of E is C. C is already here, but it has another child, which is H. Okay, so I will put H on top. Okay, then I look at H. The child of H is E. Now E is already in the stack, but G has not been placed in the stack. So I'm going to place G on top. Then I'll pick G. G will give me F. I don't have F in the stack, so I'm going to place F on top here. Then I'll pick F. F will give me C and G. Now C is already here, and G is already here. So I'll backtrack, because F doesn't have any more siblings. So I'll backtrack. I'll come down to G. G gives me F, H, and S. F is here, H is here, and S is here. So I'll backtrack again. I come to H. H gives me E and G. E is here, and G is also here. So I'll backtrack. I come to E. E gives me C and H. C is here, and H is here. So it means I don't have anything here to help me. I'll backtrack. Now I'll come back to C again. Now C, let me check all the rest of the members. D, E, F, and S. D is here, E is here, F is here, and S is here. So it means that C doesn't have any more to add to the stack. I come back to S, A, C, G. A is here, C is here, G is here. So I backtrack. Okay. Then I come to A, and A gives me B and S. And again, it means that I do not have anything else to add. When you realize that you backtrack all the cells, then the order of DFS becomes the order you got in a stack like this. So we are going to pick A. From A, I'm going to go to B, then I come to S, then I come to C, then I come to D, I come to E, I come to H, then I come to G, and then I end at F. So if you check the order, look at the two orders, okay? it started changing from the fifth vertex for DFS. Okay, this is D, E, H, G, F. This is G, D, E, F, H. So this is the difference that occurs with DFS. So please go all over the DFS. I'll do that. Okay, this is my last example. So I'm saying that, let's say that you are asked to do DFS. You take the roots that have been given. The root is A. So you place A at the bottom. And the rule for DFS is go depth. That means I pick the first child and go and pick the child's child. That's how you do it. So A, we pick the first child, which is B, and I place B on top. Now go and look at B's children. It has A. Now, A is already in the stack. It means B doesn't have anything to add to the stack. So I'll start with backtracking. I'll backtrack to A. Okay. And Sadiq, you've raised your hand. Mohammed, what's your question?
Hello, sir.
Yes, I can hear you. Go ahead.
Somebody, so for the
your network is bad. Can somebody hear him and repeat? Or you would type your question so we can read. Sadiq, if you can type your question so that I can read it and see if I can answer. But the difference of BFS and DFS is that BFS, you pick all the children of the adjacency list. Then you go to the next one and the next one and the next one. But DFS, you pick the first child. That's the difference. Okay, so A, I pick B because A gives me the first child as B. Then I go to B. B will give me A, and A is already here. So I backtrack and come back to A. Now, because I've already picked B, I'm going to pick the next child of A, which is S, and I'll place it on top. And I go to S. The first child of S is A. A is already in the stack. So check, does he have more members or more children? Yes, S has two other children. So you can pick the next one, which is C. If it doesn't have, then we backtrack. Then we'll go and look at C. First child of C is D. I'm going to place D on top here. I'm going to look at D. The child of D is C. Now C is already in the stack, and that's the only child for D. It means I don't have anything to add to the stack. So it means I'll backtrack and come back to C and go and look at the other child of C. Now we place D when we came to C. So I cannot take the next child, which is E. And the E, I'll place it on top of D. Now, what's the child of E? Is C, but C is in a stack. But E has another child, which is H. So I'm going to pick H and place it on top here. I come to look at H. It gives me E. E is already in a stack, but H has another child, which is G. So I can now put G on top here. I come to G. G gives me F. I don't have F in the sequence, so I'll place F here. And then when I go to F, look at what happens. C, G. C is here, and G is there. So then we start backtracking. Okay, I hope you see how this works. Let me see whether, Jerome, sir, please, if we should meet something like this in exam, are we supposed to do all that you are doing? The question is, how else can you do it?
You backtrack.
If you don't do it this way, what's your question? Unless you can see any other way which you will not forget another something that does not have a child. If you don't write backtrack, you don't know what to put on top. I don't know. I don't know whether it's the backtrack that is confusing people, but
no, the backtrack is right.
It's okay. By the way, the things I'm picking the item. Okay, this thing you have to really solve more questions, and it becomes clearer. Okay, Sadiq, I haven't seen your question in the chat. Please type it so I can read it. As Sadiq, I've seen hello. Maybe you are still typing. I'll come back. So we come back to G. Now G gives me F, H, and S. Look at it. F is here, H is here, and S is here. So we backtrack.
Yes.
We come to H, gives me E and G, and if it's there, then we backtrack.
Yeah.
Okay.
Yes.
We come to E. E gives me CH, and C is here, H is here. It means we backtrack. Now we are back at C. C that had so many D, E, F, and S. Now they are all there. We have D down here, E is here, F is here, and S is there. So again, all the adjacency members of C has been, so we backtrack. We come to S. It gave me A, C, G. A is at the bottom, C is at the top here, and then G is also at the top. Also, we backtrack. And then the last one is A. A gives me 2, B, S, and they are all there, B and S. We backtrack. So this is how the backtracking you must finish backtracking. If everything has been backtracked, that means you are through with the search and then visiting of the adjacency list. And then you can write your list. Okay, Hammond, I see you. Hammond, what's your question?
Hello, sir. Please,
hello.
Yeah, I wanted to know if, let's say, C, when I take C, and then the children, D, E, F, and then X, and then I don't start from D, E, F, X. I start somewhere F, X, E, D. That's how my arrangement is. Is it going to affect the BFX and the DFX?
Yes, it will. Actually, I must be frank. One of these days when I come, I'm going to open this paper. This was actually a paper, last year's paper, and I'll show you the results people did. And you see that they were so close to the answer, but the order in which they arranged, they got it wrong. So the whole thing starts from here. If you don't arrange this, if you don't arrange this thing in alphabetical order, chances are that you get a sequence, but it will not be the correct sequence. Okay? And I have already explained the significance of what we are doing. Don't look at this as ABCs. Look at this as people's phones or people's social security numbers, whatever, something very important. And you are searching. This is a search engine. This is a search engine that is implemented in either as you Google on the internet or use any of those route finders. Okay? Sometimes using depth first search is the best way to find the best route, or BFS. I'll look at all my horizontal members, or booking a flight. What really goes on behind those websites is what we are looking at. So if you don't arrange your things in order, the way the priority set, here we are using ABCD, so our priority queue is alphabetical order. So if you miss it, Master, you get a part, but Master, that will cost you if this is a real life situation or a program you're running. So your criteria that is being used or that have been defined, you must follow it so that you come out with the right, you get a path. But just that your path may be, instead of E coming before F, F will come before E. And there's a lot of reasons why I won't mark you wrong, but I have to take some marks off. That's the only thing. Okay? It means you have an idea, but you didn't pay attention to this. But well, at the end of the day, the concept and then the idea has already been settled with you. Okay, so please, these are the topics and the graph theory. Okay, I really wish I could solve past question, but now it's 9:15. I'm now approaching the time when people are knocking my doors to stop teaching. So what I'll do is, what do I do? Let's pick one particular question that deals with, yes, the BIT paper. Where is your graph? This is a graph. This was the BIT paper 2001 last year. This is what I gave them, and I asked them to do this BFS thing. I will do the same thing to you guys, so please, I beg you, learn this thing for me. It was question number 1. I hope you believe me. I don't lie.
I trust you, sir.
No problem, sir.
Well noted.
So I gave them a BFS graph. This was a graph. And if you take your time, look, any of you type BFS algorithm on Google, you will see this graph as one of the maps. So I picked it from Google, this graph. And all I did was to add these questions. I'm giving you a hint. I beg you, don't go and play with all the graphs on Google. There are so many of them. But I just picked this one for them last year. Now draw the adjacency list, perform BFS and DFS. So let's just pick this one, and then we can I'm sure everybody can at least go home knowing that we saw one past question. So let's find adjacency list for this. Okay. So where does A go to? Look at A. A doesn't go anywhere. So you see it doesn't map to anything. Yes, where does B go to? Now this is adjacency list. So it means B goes to A. See A here. And then when you come to the vector C, C is where is C?
C goes to where
A.
That's
the only place it goes to. A.
Goes to, yes, sir.
Okay. Then when you come to
D,
where does D go to? Goes to
D
C.
goes to D. Goes to C.
E, C, and what's the last one? And E.
E.
And E. Okay. Then when it comes to E, where does E go to?
E goes to R.
H and R.
H and R.
Okay.
Yes,
H
sir.
comes before R, so please take note of that. Now let's come to F. F goes to
F.
E and G.
F goes to G.
Okay.
S, C, and G.
Okay. Now G doesn't go anywhere, so nothing here.
Yes, sir.
Now H is here. H takes you to P and Q.
Q.
U and Q. Yes, sir.
P, Q. Then when you come to P,
Q.
Q. Where does P go to?
Q.
P goes to Q.
P goes to Q. Yes, sir.
Q doesn't go anywhere. Okay.
No.
And then R. Where does R take us to? R takes us to
R
F.
goes to
R
F.
goes to F.
And then S.
S.
S takes
S
us to
takes us to
D.
D, P,
E and T. Yes, sir.
E and T. Okay. Now, so I would leave the degree of the vertices for you guys. It's not so important. So now I'm going to pick. Let me put the graph on the right. I'm going to pick the adjacency list, bring it close to me, and then we'll do BFS and DFS. That's all I'm going to do. And so let me pick the adjacency list. Okay, so if I place it here, I'm sure everybody can see. Now, so let's do BFS. Starting at S, they've given you your source. Okay?
Okay.
Now, if we start at S, look at S. Let's at the bottom here. From S, where do I go to?
D. Say D.
So S, I go to D. This BFS, so see all the members of S. D.
Horizontal. Yes, sir.
Yes, and then P. Do you agree?
Yes, sir.
Yes.
So
Yes,
taking
sir.
all this. Then I'm going to shade S and say that I have visited S.
Yes.
Now let's come to D.
D.
Look at the members of D. B, C, E.
E. Yes, sir.
So we have E already. So I'm going to add B and C.
Mm-hmm.
Okay? Because E is already in the sequence. And then I'm going to shade D. Now let's come to E. This is HR. Okay, so I'm going to add H and R. That gives me E. Now let's go to P. P gives me Q.
Q.
I'm going to add Q here. And I'm going to shade P. Then I come to B. B gives me A.
Goes to A.
I'm going to give you A here. And then I'll shade B. And then I come to C. C gives me A. And you see that I don't have anything to add. So here we don't backtrack. You just shade it. Okay? H gives me Q. Now I have Q already. And I have P already. So I'm also going to shade H. Then I come to R. R gives me F, and F is not here. I'm going to add F. And shade R. And Q will give me nothing. So I'll shade it. And I come to A. A gives me nothing. I'll shade it. And then F, C, G. I have C, but I don't have G. I want to add G. And so that is your BFS. G doesn't give me anything. So that's your BFS. Okay. Now let's do DFS. Okay, Edu, I've seen your hand. Edu, what is your question, please?
Sir, I was saying that looking at the adjacency list, the E, does it go to S as well? Because you could see that the arrow points to S from the graph.
Oh, it says, I mean, this is Google. So whoever did it, you see, look at all the arrows. The arrows are at the terminating points. So the way they've drawn it, you think it's coming this way. No, but the arrow is at the end. All the graph, all the lines, they are at the end. So it means this is supposed to be pointed at E. Okay. So that is, and in fact, when you do degree,
yes, sir. Yes, sir.
Arriving and leaving, you see that we are correct. Okay, so that is it. Now let's do DFS. DFS is the one that gets people a little bit confused. So let's try that and see. Now, so we start at S. Remember S, you're going to pick the first child. So
Yes,
S,
sir.
the first child is B. Okay, like come to the first child of B is B.
B, yes, sir.
Okay. So place B on top. Then come to
B, the first child is A.
A. Now, when you come to A, nothing. So the backtracking starts from here. Okay, so we backtrack. And then we come to B.
B.
Again, it's
So
only
you
A.
backtrack.
You backtrack again.
Again.
Now I come to D. Now
D.
D gives me B and C. Okay, because
Yes,
D is
sir.
already there. So I'm going to put C on top here. Now, then we come to C. C gives me A. A is already here. So we backtrack. Then we come back to D again. D will give me now E. Okay? So we added B and C already. So we add E on top here.
E, yes, sir.
And then we come to E. E will give me H.
H.
Now H will give me P. Okay? Now
Q
P will
will
give me Q.
Q.
And then Q will give me nothing.
Nothing.
So you backtrack. Then we come to P. P, I'll backtrack. P, I'll
Track.
backtrack again. I come to H. H is in
Backtrack.
PQ.
Backtrack.
Come to E. HR. Do I have R? No. I have H, but I don't have R. So I'll add R here. Now look at R. R gives me F. I don't have F. So F goes here. And I think that'll be the last one. Where does F take me? F gives me CG. Now C is here. And G is here. I don't have G. I don't have G. Okay.
Yes, sir.
So I'm going to put G. G is going to be the last one. And then G give me nothing. So I'll start backtracking.
Backtrack.
I come to F. CG. I'll backtrack.
Backtrack.
R gives me F. You backtrack.
Backtrack.
And then you come to E again. E gives me HR. They're all there. You backtrack. And then D will give me BCE. I think they're all there. B is here, C is here, and E is here. So you backtrack. And then S.
Backtrack.
And you realize that that will be my sequence. So my sequence is going to be from here, S, D, B, A, C, E, H, E, H, and we have PQ, and then we have RF, and then G. Okay?
G.
So this is how BFS is done in this. Okay? So all you need to do is you just have a directed graph, and then take your time, find the adjacency matrix.
It's J. It's J. It's not Q.
Yeah, you're right, Jane. I'm using one hand to type and one hand to use the mouse. So, okay, so that is for what BFS and DFS. The rest of the questions that are in the past questions are either adjacency matrix. Look, find adjacency matrix, derive handshaking theorem. All these questions we've done a lot of them today, and then rechargeability matrix. Again, we've done that too. Okay, so all the questions you can do them if you are able to either draw the graph, find reachability matrix, find adjacency matrix, and then proof and shaking theorem. All these questions, I'm sure you can handle them based on what we've done. Okay, so, like I said, if you are able to go through these questions or these topics I have gone through with you, I mean, there is no other question, there is no other graph question I'll ask that